Hey everyone, this is a different sort of video than what I usually upload. I'm going to put it on Discord first, and I'll see how it's received, and if people like it, then I will post it to YouTube, and I'll maybe make more of these and post them on YouTube if people want to see more. This is a variant Sudoku puzzle. You've probably seen like Sudoku, like the normal 9x9 Sudoku puzzles in like a newspaper or something, like next to like the crossword puzzles and things like that. This is a smaller version of it. You can see that it's only a 6x6 Sudoku. Maybe you've seen those like on the back of a cereal box or something at some point. In a normal Sudoku, the aim is to put the numbers 1 through 9 once in every row, column, and 3x3 box. In a 6x6 Sudoku, you're trying to put the numbers 1 through 6 once in every row, column, and 2x3 box. But you can see that there's something unusual about this puzzle, namely that there are no numbers given to you in the grid, and there's a couple of other things here that you don't normally see in a Sudoku puzzle, which I'll explain in a bit. So this is a variant Sudoku puzzle. It's basically a Sudoku with extra rules. So, some of them are pretty simple, like they can have geometric constraints, like, two squares that are a knight's move apart cannot contain the same number, or something like that, or, you can have, like math puzzles, like you might have, like, a weirdly shaped, like, cage in the middle of a grid, and the numbers in that cage have to add to a certain number, right? Something like that. Or it can be a more exotic rule set like this one, and I'll explain it in a second. And it sounds super complicated, but it really isn't. This is the first puzzle in Marty Sears' Rat Run series. And so there's going to be a lot of other puzzles like this. Basically, the goal is to get the mouse. It's not called Mouse Run, it's called Rat Run. You get the rat to the cupcake by going around all of the walls and everything, subject to a few other constraints as well. I solved all of these puzzles, well, not all of them, but all of them up to where I had stopped. Over a year ago is when I had stopped solving these, just because I had more. It was sort of a busy time in my life. I think I solved like 20 of these. I've forgotten all of the solutions, of course, but I feel like there's, I've been playing variant Sudoku for a while. There's certain, strategies that I've picked up just from, experience that, will probably help me to complete these a little bit faster than before. Well, maybe not, because I'm going to be sort of explaining my thought process behind all of my steps, but we'll see anyway. Hopefully it's entertaining. So, yeah, and I'll do the rest of them if you guys want to see it. So I will go ahead and explain the rules. Normal 6x6 Sudoku rules apply, meaning, 1 to 6 in every row, column, and box. So Finks the rat must reach the cupcake. So here's the rat, here's the cupcake, by finding a path through the maze. The path will be a snaking line that passes through the centers of cells without visiting any cell more than once, crossing itself, or passing through any thick maze walls. So it could be something, it's kind of hard to see with me selecting. Actually, I'm going to get out the pen tool here. It could look something like this, for example, right? You basically have to, this is not the most direct path, but you basically have to lead the rat to the cupcake like this, without passing through any maze walls. So I couldn't do something like this, right? Oops, I just deleted a whole bunch of stuff. Anyway, sorry, I could not do this, because I'm passing through the wall right there. As well as moving orthogonally, so up, down, left, right, Finks may move diagonally if there's a 2x2 space in which to do so, but may never pass diagonally through the rounded end or corner of a wall. So I could go around this way, like that. That is allowed. But I could not do something like, I can't pass through here, right? Because I'm passing through this round, corner of a wall right there. Test constraint. So that's the usual Rat Run rule set. But there's an additional test constraint for each puzzle. In this one, Any two adjacent cells along the correct path must sum to a prime number, and I'll get back to that in a second. Also, all digits within a marked 3x2 Sudoku box that lie anywhere on the correct path must sum to a prime number 2. Okay, so what I take that to mean is, let's say I do something like this, right? Let's say that's the path. What it means is, so any two adjacent cells, so these have to add to a prime number, these have to add to a prime number, and these, 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 and these. Each of those pairs of numbers have to add to a prime number. And all digits within a marked 3x2 Sudoku box that lie anywhere on the correct path must sum to a prime number 2. So it would mean that these 6 have to add to a prime number. These 2 have to add to a prime number, which they would anyway. These 3 have to add to a prime number, and then these 3 also would have to add to a prime number as well. And so what a prime number is any number that cannot... Well, okay, if a number can be written as the product of two numbers other than 1 and itself, then it's composite. It's not prime. So 8 is composite because you can write it as 2 times 4. 9 is composite because you could write it as 3 times 3. 10 is composite because you could write it as 2 times 5. But 11, there's no way of doing that apart from the trivial, 1 times 11. But there's no other way of writing 11 as the product of two numbers. So 11 is prime. 12 is not because you could write 2 times 6 or 3 times 4 or 1 times 12, but we don't care about that. And then 13 is prime and so on and so forth. Okay. So if you guys want to try this puzzle before I actually start on it, then you can play using the link that I'll pin in the comment section below. There's also a few nice quality of life settings in here that you can import. I'll, copy and paste that there too, as well as the color palette that I use, although it's not really any better or worse than the default color palette. I just like using this layout because of the way that I associate certain numbers with colors, and then the pen tool and things like that. So anyway, this is your last chance to try the puzzle before I actually start. So I'm going to restart the timer, and I'm going to begin in 3, 2, 1, start. Okay, so what I do remember, actually 2 things that I can say immediately from this. Number 1, something that I do recall helping me out quite a bit when solving these for the first time was, I remember that it was pretty helpful. That gray is too similar to the box boundaries. I'm going to do it this way. I do remember that it was helpful to have basically... what I would do is I would fill in every possible grid, connection between 2 cells. I guess I gotta fill in the diagonal ones as well, don't I? And what I would do is I would delete them as I would bold them in black once I realized that they were necessary to add to the path like this, right? Or I would delete them if I found that they were impossible to use on the path, right? To just help me keep track of where the rat can go. And then the second thing that I noticed, and you may have noticed that I noticed it during when I was explaining the rules for the first time, and this is the first actual logical deduction that I can make here, is I can tell you immediately that none of these cells are used. The rat cannot go around this way. The rat's got to get out somehow. In fact, we can go ahead and fill this in. We know the rat is going to travel from here to here. Actually, we can fill this in as well. But what I can tell you for sure is that he's not, I shouldn't say he, it is going to travel around this way. That cannot happen. And the reason for that is, well, I'll show you by way of contradiction. Suppose it did travel around this way. Well, because of our test constraint, these 2 have to add to a prime number. Okay, that's fine. So do these and these and these and these and these. But what was the other rule? It says all digits within a marked 3x2 Sudoku box that lie anywhere on the correct path must sum to a prime number 2. So that would mean that these 6 numbers, whatever is in these squares, has to add to a prime number. And that's a problem, because every row, column, and box contains the numbers 1 through 6 exactly once. So I know that these 6 squares contain the numbers 1 through 6 in some order. I don't particularly care what order. But the numbers 1 through 6, 1 plus 2 plus 3 plus 4 plus 5 plus 6 is 21, which is not prime because it can be written as 3 times 7. So if it did travel around this way, I don't care what happens down here. This is not possible because there's no way of having these 6 numbers add to a prime number because they have to add to 21, which is not prime. So I can actually delete all of these connectors here. Those cannot be used, and actually that does mean that the rat has to travel this way. Okay. Oh, you know what else we can say? I don't know how exactly it's going to get around this box, but it definitely has to use this path as well. Okay. So it's definitely going to go the long way around like that, or it's just going to go straight through and just pick up those 3. Oh, you know what? It definitely, for the same reason as I mentioned up here, it also is not able to travel around this way, because, okay, let's say it did. If I use this square, I have to use this one, and this one, and this one, and I already know that these 2 are used. Sorry, you probably are seeing me like do a bunch of fancy stuff on here. I'll explain the controls. Well, I'll explain them later when I get to them. But this is not possible, again, for the same reason as before. Even though I can do some stuff in between, I can come out here and then go back into this box, these 6 squares would still have to add to a prime number, but they can't because they have to add a 21. So I definitely am not able to go the long way around this way. And just, you know, like, if I can get rid of this path, I'm sort of taking this as a given, but of course there's no dead ends apart from where it starts and where it finishes, so I definitely can't use this one, or this one, or this one. I can use this square, I just can't travel from this square to this square, right? I can now fill these in. It must go this way. And, hey, this is interesting. I do not think it is possible for... Yeah, I cannot ever visit this square, because these 5 must all be used. If I were to throw the 6th one in there, that runs into the exact same problem. It would add to 21, which is not allowed. So this square cannot be visited, and therefore I can remove all connectors leading to it. Okay, so what does that leave us with? Well, actually, I guess we can say that these squares must be visited. I don't actually know if the rat goes around like this and then down here, or if it jumps diagonally across and then goes around here. I haven't figured that out yet. So what else can we do? Oh, actually, no, we can, because if it went around this way, again, same problem. These 6 squares all lie along the path in the same box, and so they would have to add a prime number, but they can't because they have to add a 21. So we can eliminate these. It must jump diagonally across like this. And that is going to be very constraining because these 5 numbers have to add to a prime, and these 5 have to add to a prime, as well as every pair of numbers along the path, like this. Right? So what are the different... Okay, so here's where I'm going to sort of break out the fancy notation here. So all 6 numbers added together add to 21, right? Now, I'm going to ask you, can this square be a 1? It cannot, because these would have to make up the other 20. But 20 is not prime, so that does not work. So that's not a 1. It could be a 2, because that would leave 19 for these squares, which is prime. It could not be a 3, because that would leave 18. It could be a 4, because that would leave 17 for these, and that works. It can't be a 5, because that leaves 16, and it also cannot be a 6, because that leaves 15, which is not prime, because that's 3 times 5. So this square has to be a 2 or a 4, and the way that I'm going to denote that is if you click right here, or if you hold Control and then I type 2, 4, what that means is this square must contain the number 2 or 4, right? It doesn't mean that the 2 in the box has to go here or that the 4 in the box has to go here, but what it does mean is this square cannot be anything other than 2 or 4, right? And by the same logic, we can limit this square to 2 or 4. Okay, that's what it means if I put more than one number in the center of a cell like this. Okay, what else can we get? Okay, so let's see here. I remember I solved this in like a half hour the first time, but I am kind of stuck. What we actually can say is that if the rat travels around the long way around this box here, then we have the same 5 out of 6 situation, and we could also put a 2, 4 mark in here, but we don't know that it goes this way around. It could go this way, right? What else can we say? Let's see here. Like, I also know that the rat is not going to consume all 6 squares in this box, but there's not really any way of denoting that, and it doesn't really narrow anything down anyway. Alright, I actually have to think. Maybe we should start working on this constraint, the one that says that every pair of numbers along the path has to add to a prime number. That'd be a good place to start, actually. Because let's think about what all our prime numbers are. So 1 does not count as a prime number by convention, but 2 is. And then 3, 5, 7, 11. Oh, you know what I'm going to do? So I've done this before. Sometimes it's helpful to me to color a Sudoku puzzle. What I'm going to do is these squares must contain a 2 or a 4, just based on the way that prime numbers work. Almost every prime number is odd. 2 is the only even prime number. The rest of them are odd. And so I can tell that this is going to be an odd-even puzzle. So what I'm going to do is I'm going to color these 2 squares blue, and any square that I know contains an odd number I'm going to color in yellow. And we'll see if that helps. Because the reason that I say this is because I happen to know that if I ever add 2 even numbers together, I get an even number. If I ever add 2 odd numbers together, I also get an even number. The only way to get an odd number is to do one of each, to have an even and an odd. That's the only way that you can add 2 numbers and get an odd number, right? And to me, that feels extremely limiting here. Okay, so here's something that I can say. So 2 is an even number that is a prime number, but I can't have 2 numbers that see each other that add to 2. I couldn't be like, oh, maybe, you know, these add to 2, or these add to 2, or these. Because how can you add 2 Sudoku numbers and get a 2? The only way is 1 plus 1. But I can't put a 1 in both of these. Whoops, sorry. I can't put a 1 in both of these. Oh, I have the conflict checker on. Let me turn that off. I thought I already did. Conflict checker, it is off. What the heck? I swear I fixed all of these settings. Check on finish, mark selected. It's off. Oh, check pencil marks off. Sorry about that. Or that's not even, no, it's not check pencil marks. It's just not going to let me put a 1 in both of these. I don't know why. I know that it's wrong. I'm just trying to show you for the sake of demonstration. How do I, constraint alert? No, how do I do this? How do I turn off solve digits, check on finish. I'm not finished. Whatever, I'm just going to leave it. Oh, there we go. Whatever I did, solve it. Okay, so I can't put a 1 in both of these because the ones see each other, by which I mean they're in the same box, and in fact the same row. So I can't be like, oh, maybe these add to 2, because the only way of getting to 2 is 1 plus 1, right? So maybe it's like a 1 and a 2, because that adds to 3, or maybe it's a 3 and a 2, because that adds to 5. That's a prime number. I could, what's the biggest prime number? I guess it'd be like 5 and, whoops, yeah, I could go like 5 and 6. It's the biggest prime number you can get with 2 Sudoku digits in a 6x6 Sudoku. That's 11, that's prime. So I could get to, I guess I could get to 3, 5, 7, or 11. In fact, those are the only pairs that are possible. I can't get to 2 because it's 1 and 1, right? Now, that means this, so let's say this pair of numbers has to be odd, this pair of numbers has to be odd, this has to be odd, and this has to be odd, right? Now, the reason that's important to me is I can never have 2 odds in a row or 2 evens in a row, because they would add to an even number, which is not prime. I can't have 2 even numbers here, because they would add to an even number. That's not prime. I can't have 2 odd numbers here, because that would add to an odd number, and that's not prime. Or sorry, they would add to an even. 2 odds add to an even, which isn't prime, right? Okay. But what that means is this has to contain an odd and an even, this has to contain an odd and an even, this has to contain an odd and an even, this has to contain an odd and an even. What that tells me is they have to alternate. It has to go odd, even, odd, or maybe it goes even, odd, even, right? It has to be one of those 2 configurations. Now you tell me which of those is impossible. This is one possible arrangement. This is the other. Which of these is not possible? This one's not possible because I don't know which numbers go where, but what I've got in this box now is I have to put the digits 1 through 6 in every box, which is 3 evens and 3 odds, but this box has 4 evens and 2 odds. That doesn't work, right? Like, if I put the 1 here and the 3 here, where would the 5 go? All of the others have even numbers in them, right? So that doesn't work. It has to be the other way around. It has to go odd, even, odd. And then same thing here. This is just the mirrored version of that. This cannot go even, odd, even, because that's too many evens in the box. It has to go odd, even, odd, right? And actually, I've just now spotted something interesting. You might say, isn't that a problem? Because these 2 squares have to add to a prime number, but they're both odd. Now, how can I add 2 odd numbers and get a prime number? I just mentioned this earlier. The only way of doing that, well, 2 odd numbers add to an even number. The only even number that's prime is 2, and the only way of adding 2 digits to get to 2 is 1 plus 1. So I have to put 1s here. That's not a problem because these 1s don't see each other. They're not in the same row, column, or 2x3 box. This is totally legal. I couldn't put 1s here, but I can put 1s here. They see each other diagonally, but that doesn't matter, right? Okay. And so that means this is 3 or 5. This is 3 or 5. I guess I can go ahead and mark the whole box. In fact, I'm going to select all of these. These are all 2, 4, or 6. These are both 3 and 5. I don't exactly know how. Okay. Actually, another thing I can do, these 2 have to add to a prime, and since, again, they see each other, they're in the same column, I can't do the 1 plus 1 equals 2 trick, so this is going to have to be even. This is going to have to be even by the same reason. This has to be an even and an odd or the other way around, but I'm not going to mark that. What else can I say? Actually, maybe I'm not going to mark the 2, 4, 6, because, of course, I can just mark that by putting a blue square there. I don't need to do anything special, because those are the only even numbers. What else can I say? I guess this has to be an even and an odd. So this is one of each, and actually this is one of each, so this also has to be one of each in order to get 3 evens and 3 odds in this column. Again, there's not really a convenient way of marking that. Huh. Well, no, here's what we can do. Let me think about this. Okay, yeah. I've noticed something interesting. So I want you to consider what numbers can go in this square. Obviously, it has to be 2, 4, or 6. But in fact, I can tell you right now what number goes in here. And the reason is because either this is a 3 and this is a 5, or the other way around. It's one of those two configurations. Whatever number I put here, though, suppose it's a 2. It has to be a prime number if I add 3 to it, and if I add 5 to it. So 2 plus 3 is 5, that's prime, that works. 2 plus 5 is 7, that's prime, that works as well. So if this is a 3 and a 5, that's legal, or if it's a 5 and a 3, that's legal. These have to add to a prime, and these have to add to a prime, right? Very good. Okay, but why does it have to be a 2? Consider what would happen if I put a 4 here instead. That does not work, because 4 plus 5 is 9, which is not prime. So wherever the 5 is, I'm actually not sure where the 5 is, but I don't care. It's one of these two squares. Whichever of these two squares it is, it would combine with this 4 and make a 9, which is not allowed. It's either 3 and 5 this way, and oh, we have a 5 plus 4 is 9, that's not allowed. Or it's a 5 and a 3 this way, and now we have a 5 and a 4, that adds to 9, that's not allowed. So whichever way around the 3 and the 5 go, I'm not sure, but whatever it is, this can't be a 4, and for the same reason it can't be a 6, because it would combine with the 3 wherever the 3 is to make 9, right? So the only even number left is a 2. And in fact, this has to be a 2 as well, and that's nice because this 2 sees... Remember how I said this had to be a 2 or a 4? Well, now I can say for sure it's a 4, and that's also a 4, and this is the only even spot left, so that's a 6, and that's a 6. I still can't resolve the 3s and 5s, but that's okay. Oh, actually, I can. I can resolve the 3s and 5s. Can you spot how? This is the square to look at. What does this have to be? It can't be a 3 because 6 plus 3 is 9, and that's not prime. So that must be 5, and that must be 3, and that 3 sees this square, or you could just do it this way again, and that's going to be a 5, and that's going to be a 3, right? Okay. I can also now say this... Well, it's an even number. It's not 2, because there's already a 2 here. It's also not a 6, because 6 plus 3 is 9, and that is not prime, so this must be a 4, and this must be a... wait. No, sorry. I selected the wrong square by mistake. That's a 4, that's a 4. I feel like this coloring has served its purpose. I may go back to it, but I think I'm going to delete them. Okay, what else? Well, alright, let's just do some regular Sudoku techniques. So where does the 4 go in this box? It can't go here because it sees this 4. It can't go here because it sees this 4. It's got to be in one of these two. Oh, actually, no, in fact, it has to be here, right? Because this sees that 4, right? This is the only square in this box that... does not see another 4. Same thing down here. This is where the 4 has to be, right? Okay. In fact, we're done with the 4s now. What else can we do? I mean, I can mark, like, you know, 1, 5, 6 here. I don't need to, though. It's I don't want to clutter the grid any more than it already is. Let me think about something here. Yes. Yeah, so I've spotted something else. is this an even or odd square? Again, within a box, I have to alternate odd, even, right? Odd, even, odd, even, odd, even. This is even, right? Well, whichever way around I go, whether it's this way or the long way around, if this is even, that's odd, and then that's even. But if I go this way, this is even, that's odd, that's even, that's odd, that's also even. Whichever way I go, that's even. So that has to be even, that's odd, that's even. In fact, I'm not going to go back to that coloring system. I'm just going to say that's definitely a 2 or a 6, because it can't be a 4, obviously. That's got to be a 3 or a 5, because it can't be a 1, and that's also a 2 or a 6. Okay. What else can we do here? So this is not a 6-3. 2-3 is fine, 2-5 is fine, 6-5 is fine, 6-3 is the only one that doesn't work, right? But I don't really have any good way of marking that. Oh! Well, so here's something else to notice. Let's say that I go the long way around, and I go even, odd, even. This adds to an even number, right? 3 evens and 2 odds. Think of it this way. These odds, they add to an even number. I don't know what it is. So I have that even number that I've got as a result of adding those 2 odds, and then I've got another even, another even, and another even. That's an even plus an even plus an even plus an even. Of course, that has to be even, doesn't it? So it can't go the long way around. That does not work. It has to go this way. So this part of the path is unused. So what odd number can I... Well, it can't be a 5, because 5 plus 4 is 9. But 3 works, because that's a 7, and then 1 works, because that would be a 5. So either of those is okay. What else? That doesn't really feel like it helps all that much. If I put a 2 here, does that mess anything up? It would force a 6 into here and here, and that forces this to be a 5. That's fine, because that's 11, 11. That has to be 1. It can't be a 3, because then it's a 9 right here. So that's got to be a 1. That would be a 3. This would be a 2. I don't think that messes anything up. I mean, this would be a 3, that'd be a 5. I don't want to just, like, keep solving until I get to a contradiction, though. I don't want to do it that way. I was trying to see if... Because if this is not a 2, I already know that's a 2, so the 2 would have to go there in this column. But I can't say that just yet. What else can I do here? Maybe just regular Sudoku tricks. So one's got to go here. It's got to go here. Here. Doesn't really help. Two's got to be either. Okay, so I'm actually going to do something here. So I'm gonna do a corner mark. So what a corner mark means, it's not saying this square must be this or that. It's the reverse. It's saying wherever the 2 is in this box, it's either here or here. It can't be here, can't be here, can't be here, certainly can't be here. Right? The 2 in the box is one of these 2 squares. When I say 2, 6 like this, it means that the number in this square is either a 2 or a 6. Right? Does it make sense, the difference between those 2 things? Anyway, so the 2 has to be in one of those. I'll come back to that. Maybe it'll help. I have to have a 2 in one of these. I could mark them like that, but I don't really want to. Oh! I've just now spotted something really interesting. Where's the 3 in this box? It's not here, because there's a 4 there. It's not here, because we've already said it must be a 2 or a 6. And it's neither of these, because it sees this 3. So the 3 in this box must be in one of these 2 squares. It's got to be here, or it's got to be here. Now, this cannot be a 3 anymore. Because wherever the 3 is, whether it's in this square or this square, I don't care which, wherever it is, it's going to see this 3 and knock the 3 out of there. Right? If this was a 3, I can't put a 3 there because they see each other. And if this is a 3, I can't put a 3 here and they see each other. And it's the only 2 places that a 3 can go in this box. Another way of thinking about it is the reverse. What would happen if I did put a 3 here? Well, then there's nowhere to put a 3 in this box, right? This is occupied, this 3 sees those, and this 3 sees those. And now I've run out of space. So that cannot be a 3. I don't know which of these has a 3 in it, but whichever one it is, this can't be a 3, so that's got to be a 1. That actually is going to put a 1 here, because that's the only place in this box for a 1. Because this 1 is going to knock it out of these 2, so it's got to be there. And it's also going to put a 1 in one of these 2 squares in this box, because this sees those, so it's got to be one of these 2. I don't know which one it is yet. In fact, when I am limited to 2 numbers, like 5, 6, 5, 6, in this column, for example, I will mark it. This could be a 2 or a 3, couldn't it? Yeah, it could. I'm actually going to get rid of the corner marks now, because the center marks already say everything that the corner marks do. In fact, these have to be the same number, don't they? Because whatever number this is, I'm just going to color it green. Where is the green number in this box? Well, green certainly can't be there because it sees this green. It can't be here or here because that's 1 and 4. Those aren't green. This has to be green. In fact, I'm going to label them like this just to show that they are the same. Maybe I won't use green. Maybe I'll use like just brown or something. Yeah, I'll use brown. Okay, what else can we say here? So they're both 2s or they're both 6s. Well, no. I was going to say, hey, if this is a 2, then these all add to 7. If this is a 6, then these all add to 11. Either of those are prime. That's fine. And likewise, you know, it's not going to be any issue over here either. Okay, what else can we do? Oh, well, you know what I can do? Is it possible for these 2 to connect? Can the rat take this path down here? It cannot. Because what would this square be? It can't be a 5, because then that adds to 9, that's not prime. It can't be a 6, because then adds to 10, and that's certainly not prime. So this cannot be... I cannot use this connector. I could, like, you know, do a little zigzag here and come back to it, but I can't use the path that goes from here to there. That's not allowed. Okay. I mean, that doesn't really help us, but it's something. I guess I'll go ahead and mark this box as well. What are these? 2s, 3s, 5s, and 6s. This can't be a 2 or a 3 because it sees those. This can't be a 5 or a 6 because it sees those. This can be pretty much anything. Well, okay, let's again look at this column now. Where does the 1 go in this column? It has to go here or here. So that is the 1 in this box. The 1 could not go somewhere else in this box, well, for 2 reasons. One is the obvious reason, because these 1s eliminate them, or the other, like, weird reason that for some reason I noticed first, which is that if a 1 were to go in here, there's nowhere to put a 1 in this column, because the 1 couldn't also go there. But I can now say the 1 goes in one of these 2 squares. Okay, let's look at maybe 2s. So there's 2, 2, does not really help. Let's look at 3s. Not very helpful either. Fours. Oh, I'm done with fours. Fives. I can't really do anything with fives. I mean, I know a five has to be in one of those three, but I'm not going to mark that. And then sixes. Same thing. Can't really do much with that. Oh, man. Okay. Oh, well, I guess I can say that this is a 2 or 3. Because, you know, I've already used 1, 4, 5, and 6 in the column, so those are both 2 and 3. In fact, they're different. What is this, then? I guess it could be basically anything. I wish I knew if this was odd or even, though. Having it be a 2 and a 3 is kind of annoying. Can't do much with that. I'm going to try a different technique here. It may not be helpful, but you never know. I'm going to try... Let me just color the whole grid like this. I'm going to checkerboard the grid, and because I've noticed something... Here, for this portion of the path, evens are orange and odds are green. But then from here on, evens are orange. Or no, wait. No. Yeah, no, evens are orange and odds are green. In fact, I'm just going to go ahead and select all the oranges and make them yellow, because that's kind of my... Well... Does this really mean anything? I'm trying to think of, like, the parity between, like, how many diagonal moves I make between here and here. Maybe that's not helpful. Yeah, that's probably a waste of time. I figured it would be. Oh, I gotta mark these again. Okay, what else can I say? This is tough. I feel like this is where it wants me to look, but I can't quite see how. Well, so, Or maybe actually there's something up here I want to look at real quick. That's a 2. That's a 3, that's a 5, that's a 6. Yeah, okay, let's say I make this a 6. This can't be a 6, so it's a 5. This can't be a 5, so it's a 3. This can't be a 3, so it's a 2. That doesn't work, because 6 plus 3 is 9. So it must be the other option, which is that this is not 6, and therefore it's a 2. That does not mean this is a 5, it just means it's not a 6-3. Because 2-3 is fine, 2-5 is fine, 6-5 is fine, 6-3 is only one that's not fine. Also, we said this is the same one, so those are also, that's also a 2. Well, actually, now we can say that because that's a 2, that's a 3, that's a 5, that's a 6. We can do the same thing up here. That's a 2, that's a 3, that's a... Well, it's not a 2 or 3. I guess we can't actually sort out the 5s and 6s up here, but that's okay. We can say, though, that these are 3 and 6, and these are 1 and 2. Oh, so where does the 5 go in this box? It can only go here. Alright. Oh, and this is now a 2 because it sees that 3. Oh, and that 2 sees this 2, so that's now a 1. That's a 2. That's not a 1. That's a 1. Am I going a little bit too fast? Sorry, I'm just used to kind of sight reading these, but... So this 3 sees that, so that has to be a 2. This 2 sees that, so that has to be a 1. So the 1 and the 2 go this way rather than the other way. Then this 1 sees this 1, so that's not a 1, so that's the 1. And that's as far as we got. So this is a 3, 5, and a 6. I'm just going to put them in because that's all we got left. Whoops, no, meant to do it the other way. That's a 3, 5, or a 6 somehow, except that's not a 3 because it sees this one. That's all I know. Oh, well, actually, what we can say is this has to join with a 2 to make a prime. So it's not a 6. It's got to be 3 or 5. Because 3 and 2 is 5, 5 and 2 is 7, but that's all we can do. What else? Well, I can't go 4 to 2 because that's 6. I can't go 5 to 1 because that's 6. I must now go here because it has to go somewhere. This is now a dead end, so it can't be used. I could go 1 to 2. I could go 1 to 6, wherever the 6 is, but I don't know where the 6 is. I can't go 1 to 3, because that's 4. Oh, that can't be a 5 anymore, because it sees this 5. Now what? It's something to do with these... Oh, well, you know what I can say? This cannot be used. This connector right here. Because it would connect a 3 to a 6 or a 6 to a 3. Either way, that's 9. It's not allowed. Actually, I can't use this either, because that connects a 3 to a 6. I also cannot use this. It either connects a 3 and a 6, which is 9, or a 3 and a 3, which is 6, or a 6 and a 6, which is 12. None of those are prime, so there's no combination of numbers I can put on either end of this connector that makes it usable. So that has to be out. That makes this a dead end, so it can't be used. No, I was about to say something that didn't make sense. I'm so close. Oh, well, you know what? Yeah, okay. Let me ask you a question. Can the rat use all of these squares in this box, just leaving out the 5? No. Because 4 plus 1 plus 2 plus 3 plus 6, whatever order you add those in, that adds to 16. That's not prime. Remember, the numbers, all of the used numbers within a box have to be add to a prime number as well. 16 is not prime. That's the very first thing we used to eliminate this path, remember? So I cannot use all of these, but I must leave out something. I cannot leave them both out because this has to lead somewhere. I must leave one of them out. Okay, so I'm not sure. This is going to be a little bit of a complicated piece of logic. I've just realized how to solve part of this, but I want to see if there's a more straightforward way of looking at this first. If I don't see it, then I'll use the fancy logic. Okay. So, okay. Well, here's something. Yeah. Wherever the 3 is in this box, it can't be on the path. Because what would it connect to? We've already said it would not connect to the 6 that's next to it. Oh, no, we could, actually. Yeah, it could be used, because it could connect to the 2. Yeah. Okay, I am just going to use my complicated piece of logic, and maybe there's a simpler way of solving this that you guys will correct me on, but This is the way that I noticed it. I know that the 4 is used, the 1 is used, and the 5 is unused. I'm not sure about this 2. Right? I did say... Oh, hold on. Yeah, okay, is it possible for me to use the 4, 1, 3, and 6, and nothing else? No, because that adds to 14, and it's not prime. Actually, here's the easier way of looking at it. Let's think about the unused cells in this box. Now, 21 is what they all add to. The used cells have to add to a prime number, which is odd, because it's not 2, of course. So the unused cells have to add to an even number. Because... Yeah, this is a much simpler way of looking at it. The used cells plus the unused cells add to 21. Right? The used cells plus the unused cells add to 21, because that's all of the cells in the box. This box. Now, 21 is odd. So, and the only way of adding two numbers and getting an odd is an odd and an even, one of each. So, either the used cells add to an even number and the unused cells add to an odd number, or vice versa, right? Because we can say used plus unused equals odd. So it's got to be even plus odd or odd plus even. But the used cells have to add to an odd number because they have to add to a prime number. And it's not 2. So if the used cells add to an odd number, the unused cells have to add to an even number. So what cells are unused? This is a 5. So far, it's the only one that I know for sure is unused. I have to make it even somehow. Adding the 2 doesn't change its parity. It doesn't change whether it's odd or even, so the 2 doesn't really matter for now. And adding the 6 also is going to... That doesn't change whether it's odd or even, right? But I have to add the 3 to it. The 3 has to be unused. It has to be 5 and 3. That's 8. That does make it... That flips it to even, because 8 is even. The 2 and the 6 may also be unused, right? That'll keep it at an even number, right? But what I can say for sure is that one of these 2 is used, but I know the 3 is unused, so the 6 has to be used. And the reason that it's important that the 6 is used, and that it's one of these 2 squares, is because it connects to this square. Wherever the 6 is, it's on the path and it connects to this square. So 6 plus something, that has to be a prime number, so therefore this cannot be 3, because the 3 would connect to wherever the 6 is, it has to connect to this 3, but that's a 9, that's not allowed. I don't know where the 6 is, but it's being used, because the 3 has to be unused. So that cannot be a 3, it must be a 5. That makes this a 6, this a 5, this a 6, this a 3, this a 3, this a 6. Oh, I didn't actually finish the path. Experiment completed successfully, cells visited 20, Finks is already showing tenacity and increased cognitive abilities, ready to progress to a larger maze. That's cute. We might do the next one if you guys liked this. Let me go ahead and actually finish the path, though. So this is the... Okay, let's see here. We can't connect a 2 to a 6. We said we didn't use the 3, so we can destroy all of the paths. Yeah. We can destroy all the paths connecting to the 3. This is now a dead end, so it must look like this. There we go. Okay, let's just double check our work. 7, 7, 3, 5, 7, 5, 7, 11, 7, 2, 7, 11, 7, 5, 7, 5, 7, 11, 7. And then this is 7, this is 7, this is 17, this is also 17, this is 11, and this is 7. Okay, looks good. Nice. I mean, it already checked it for us. From now on, I'll actually complete the path before filling in the last few numbers. But anyway, there you go. I hope you guys enjoyed. If you didn't, then, well, I guess this is never going to make it onto YouTube, because if my most dedicated followers who are in my Discord server are not going to enjoy it, then I imagine the general public probably will not. But anyway, let me know what you thought, and if you'd like to see more of these. I hope you had a good time solving this on your own. If you did, yeah, I'm not quite sure how to end this, but yeah, I'll see you next video. Bye.